ஒப்பிக்க முடியாது.
Hello, welcome to the second lab session of quantity topology 1 course. Sorry, it's not 2 here, it's actually 1. It's my mistake. Okay, so this is the second lab session. So first, let me introduce myself. I am Shavik and I am working at performance casting at IIT Madras. So before proceeding further, let me know if you can see the screen and can you hear me properly. Please let me know, am I audible and can you see the screen? I have shared a screen of OneNote.
Yes, sir, you are audible and the screen is visible.
Okay, thank you. Okay, so okay, so on the last day itself, okay, one second. So as per I can see is that possibly at least one of you has not attended the last session. So one second, just hold a second. Yeah. So if you have any issue or any doubt from the last lab session, you can ask me in the meeting itself, or you can do a mail. No problem. I will reply. So yeah, I got the chat here. Check the chat. Yeah, coconut topology. I have to check the closure. Yeah, we'll get into those things. Okay. I mean, don't worry. We will do problem solving, and the question you have asked, we will do it also. But there are some theoretical aspects. First, we'll finish those. Then we'll slowly go into the problem solving session. Okay. So one second. Okay. So okay. So till in the last session we have gone through the introduction of introduction of topology, and finally we saw some examples, and we have gone through the basis thing. Okay. So today we'll start with the product topology. Okay. Before starting, anybody please tell in the in Sastry sir till now what part of he has done in the main course. Till now, which part has been covered by Sastry sir? Anybody please? Okay. Okay. So okay. So let's start with the product topology. Okay, since I'm starting to write, so I couldn't see the chat actually. So if you have any doubt, you can unmute yourself and ask the question. So the first thing comes here is known as the product topology. Okay. So this is defined as follows. Suppose x star 1, sorry, and y tau 2 are two spaces. Then we can define tau 3 as u cross v, where u belongs to tau 1, v belongs to tau. Then x cross y, endo with the topology tau 3, called the product topology on x cross y. Okay. So whenever we are talking about product topology on x cross y, this means that there is already given topologies on x and y itself. Okay. And how the product topology has been made, the constructed, the open set of open set of x cross open set of Cartesian product of open set of v. This type of sets we are defining to be, sorry, it's my mistake. Sorry. Okay. So we are defining tau 3 to be all those elements of the form u cross v. Now the topology generated by tau 3 of x cross y is called product topology. Okay, so let me explain why suddenly I have changed the definition as the topology generated by tau 3. Okay, because initially I wrote that that tau 3 forms the topology and it's known as product topology. Why suddenly this topology generated by tau 3 came? The thing is, if you consider R2, R2 can be written as R cross R. Okay, the point is that you R cross R is of the form. Now any open set of R is nothing but an open interval, and same here also, open set of R is an open interval. So if call it you call it V, then this is some kind of U cross V, and this is open in R2. Okay, but the thing is, not all open sets of R2 is of the form U cross V. For example, uh, this is an open set in R2, but this is not of the form U cross V, right? So that's why we directly not declaring that U cross V's are all open. So we are declaring the topology generated by the sets of the form U cross V is called the product topology. Okay, so this is the one thing. So the thing is that since we are writing the topology generated by tau 3 means what? We are considering, so this is not what, this is not tau 3 is a base. Okay, this is one thing. You can note it. So this is what the product topology mean. Okay. Now, okay, so product topology is defined in terms of basis itself. Okay. Also, it can be defined in another way. I mean, so, suppose look, in this case we have x tau 1 and y tau 2 given. So tau 1 in a topology has some basis. So we are defining the topology on x cross y in terms of u cross v, but it does not include directly any elements of the form. Might not include any elements of the form which comes from the basis. Okay, so we can define it the following way. Let beta be basis of tau 1 and beta 2 be basis of tau 2. Then define beta u cross v, u belongs to beta 1 and belongs to this beta is a basis for product topology on x cross y. So basically, it's a theorem or fact, whatever it is. So the thing is, if for the product topology and if the bases are already given, we can simply do the Cartesian, all possible Cartesian product between those two basic elements, and that will give a basis for the product topology x cross y. Okay. So can anybody please tell how to prove this? Look, we have already defined product topology in terms of basis elements of the form u cross v. So this is the definition. This is the definition. Okay. Now we are Now the theorem is that if we have the corresponding basis, then the all possible Cartesian product between two those basis elements is a basis for the product topology inverse Y. So can anybody please tell how to prove this? Take your time, think about it, and please tell. Whatever the argument, whatever the logic you are thinking, please tell. Think about it, please tell. Anybody?
Sir,
Yes. Yes, please tell.
in the product topology,
Yes.
hello,
Yeah. Yes, yes. Yes, tell.
if you take any open set
Yes.
and take any point in that open set, x
Yes.
comma y,
Yes.
corresponding to x, there will be a basis element in the first topology tau 1
Yes.
containing that x.
Yes.
Corresponding to y, there will be some v in tau 2
Yes. Yes.
uh, that contains. So that corresponding this u cross v, this is a
Yes.
basis element from u that contains that point and contained in that given open set.
Correct. Correct. Then.
So this is a basis for the product topology, sir.
Okay. So you are in the right track. Look that. Look. The thing is that whatever you have said in this portion, this comes from the definition of product topology itself, right? But the thing is, in the theorem, what we need to do? We need to find some u which comes from the basis, something which comes from the basis. But here u and v are some open set. You somehow come up with some base element which is contained in u and some another base element which is contained inside v. How to do that? I mean, you are almost right direction. Just think about it. Till now, you have used only the definition of product topology, right? Correct? You have not used anything regarding basis element. So you need to somehow come up with two basis elements which lies inside you and inside me. How to do that? So I mean, so you need to use this fact. I mean, the beta one is a basis for tau one and beta two is the base of tau two. So you need to use this fact. So what can you think about after reading these two lines?
So kindly explain, sir, please.
Yeah, okay. Look, the thing is that since beta 1 is a basis for tau 1, okay, this
Yes, sir.
means what? This means what?
Tau1 is the collection of unions of beta one, the beta ones.
Sorry, please repeat.
Arbitrary union of the elements of beta one
Arbitrary union of elements of beta 1 is what?
is nothing but there are all open sets of tau 1.
Okay, so you are saying that if we take any open state, then it can be written as arbitrary enough basis elements, right?
Yes, yes,
So
sir.
this is okay. So look, I mean, this is a consequence or these are theorem, but by definition, what is the basis element? So let me write it down. So let beta be a basis of X. So this means what? This means for any open set U and any X belongs to U, there exists a basis element such that X belongs to beta X subspace. Correct? These are this comes from directly. I mean, this comes from the definition of basis itself, right? This thing have you?
Yes,
I mean,
sir.
can you remember? So yeah. So this is by basis. This is what we mean usually. Okay. So what we have said in this, I mean, in this portion. So here U belongs to tau one and V belongs to tau, and X belongs to U1, X belongs to U, and Y belongs to V. So since beta one and beta two are basis, so this means what? X belongs to beta one uh, subset of U, and X belongs to beta 2 subset of V, right? Where beta 1 belongs to a basis element of X and beta 2 belongs to basis element of Y, right?
Okay, sir.
You understand? Okay.
Yes, sir. Thank you, sir.
So yeah. So so from here what we get that beta 1 cross beta 2 subset of U cross V subset of W, and of course X or Y belongs to this thing. So this belongs to our capital big beta. So this is what we want to prove, that this beta is a basis for the product topology on X cross Y. Do you understand?
Yes, sir. We understand, sir.
Yeah. Okay. So this is one thing. So this is what a product topology. So keep in mind that the product topology on X cross Y, the basis elements of the form U cross V, and where U and V can be thought as basis element or can be thought as an all possible open set. That's it. Okay. There is
Okay,
nothing
sir.
much. So okay. So yeah. So now there is another important. Suppose X and Y are spaces. Okay, by the way, when someone is, I mean, it is natural to write X, Y, and spaces in many books also. Spaces means X and Y have some topology, and we usually don't write the topology. Okay, means there is a topology. That's it. We are not explicitly mentioning it. Okay, suppose X and Y are spaces. So consider the map pi one. Yes. Okay. Consider the map pi one from X cross Y to X, which is nothing but the first coordinate projection. X comma Y goes to X. Okay. So look, okay. The theorem is that pi one is open. So this is what we need to check. Pi one is an open map. First of all, first try to understand this pi one is open map makes sense. Open map means what? Open map, we need to show that pi one takes open set to open set. Now X cross Y, we have the product topology. So there are some open sets in X cross Y. So we need to prove that pi one is an open map. So what you will do? You will take an open set of X cross Y, write the open set in terms of base elements of the form U cross V, and now apply pi one and check that pi one of that thing is open or not. Okay, understand? What you do?
Yes, sir.
Yeah, please do it by yourself. Take your time. I shall be back after 2-3 minutes. Okay, please do it by yourself. I'll be back after 2-3 minutes. আহ, না না এটা তো মটর ভাজা কে বলে? না মটর ভাজা বললো না। মটর ভাজা বলে নি বলেছে নাকি? মটর ভাজা বলে নি? না 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 মটর ভাজা তো বলেনি যতটা আমার জানা আছে। যাক এখন চাপিও না, ফোন ধরুক তারপর বলছি। এখন চাপিও না, মা ফোন ধরুক তারপর বলছি। Okay, so have you done it?
Sir, if you take any U cross V, where U cross V is an open set in the product topology, that goes to U.
Yeah.
We have to show U is open.
Yes.
Take any X in U. We have to find some BX so that
One second, one second, one second. So you have started by saying that U cross B is open in X cross Y, right? Correct? I mean,
yes,
yeah.
sir.
So the thing is that look, yeah, for the definition, yeah. So this is the definition. Topology generated by this element, this type of element, is called a product topology. So I mean, this means what? I mean, this we are treating as a basis. I mean, all open set is not of the form U cross V. This U cross V, I mean, these are the
Okay, okay.
basis.
Thank you, sir.
Yeah,
Thank you, sir. Yeah, yeah. Take any open set.
yeah,
You
okay,
take any open set. Um,
yeah, okay. Then,
yeah. Take any open set in X class Y. Actually, if
yes,
and pi one is the projection on X axis, we will
yes.
get some and let the projection be some. Let the open set in X class Y be O1
No,
and its
no,
projection
no, that's
be
what I have taken. W we open in X. W I am taking
uh,
the open set in. Then what?
W is open in X class Y. Let's
Yes,
let its projection be some W2 be some
okay,
W2. Yeah.
yes,
And let us take any point in W2, some X in W2. Corresponding to the X, there will be some X comma Y that will be in W. and corresponding to this x comma y, there will be some basis element bx comma by, bx cross by, that containing x comma y, and inside the w.
Yes.
So this bx containing x, that also contained in w2.
Yes.
Why?
Correct.
Because that's why, because w, the projection of w, projection of bx, w is a subset of that's why.
Yeah. Very good. Very correct.
So thank you. You guided me, sir. Actually, I started in a wrong way.
I mean, that's okay.
Yeah, thank you, sir.
Okay. So your argument is correct. So okay. So you have done it very nice way. Also, it can be done in quite a technical way. Okay. The thing is, so it can be done in another way. Let me write it down. So okay. So any W be any open set in X cross Y. Whatever the way you have done, whatever I am now writing, are both same essentially, but but this type of solution are quite technical. Okay, means while there are, right now you are in the first or second chapter topology. So after some chapters, there are lots of things. Okay, so at that time it is
Mm.
difficult to keep track each and everything. So at that time, this type of solution will help. Okay, so
Okay, sir.
keep so keep this mind in this type of solution also. These are technical solutions actually. So let W be an open in X cross Y. So W can be written as a union of elements of the form U alpha cross U alpha, where U alpha is open in X and U alpha are open in Y. This we can write because any open set can be written arbitrary of base elements, right?
Its projection is union of u alpha. Then that's, thank
Yes,
you, sir.
correct. Yeah. So
Yeah,
yeah, it's simply U alpha. That's
yeah.
all. Okay. So this is one thing. So this is
Nice.
like
It's a decent and elegant and neat, very neat to understand.
angle. So this is what we proved, that the projection map, the first quadrant projection map is open. Similarly, we can show that the second. Similarly, we can show
That's
the second.
also
Yeah,
open map.
that is also open. Yeah, okay. So next thing is okay. So next thing is known as the subspace topology. So what is this? So look, what we have done a product topology. We have given two spaces and we are topologizing the X cross Y. Okay, and subspace topology almost same thing but slightly different. Subspace topology, as the name suggests, we are giving a topology into a subset. That's it. So let X tau be a space and let Y is a subset of X. Now we are trying to give a topology on Y. How do we? So we are giving tau Y, we are defining tau Y to be U intersection Y, where U is open in X. Check that it is indeed a topology on Y. So in subspace topology, what we will do, we have some bigger space. We are taking a subspace and we are defining the open set of the subspace to be all possible open set of X intersection that subspace, and check that this collection U intersection Y forms the topology on Y. This topology is known as subspace topology. Okay, so there's a definition. So remember one thing in the product topology. Yeah. In the product topology, we have defined the product topology in terms of elements of the form U cross V, such that a topology is generated by those things. The U cross V forms a basis. But in the subspace topology, we are directly defining the topology by taking the intersection of all possible open set with the subset itself, and this is known as the subspace topology. Do you understand definition?
Yes, sir. Thank you, sir.
Okay, so this is the definition of subspace topology. So what about the definition in terms of basis? Somewhat like we have seen in the product topology also. So so suppose suppose let beta be a basis for tau. I mean for x tau. Then we are defining beta y to be naturally b intersection y, where b is an basis element of x, and check that beta y is the basis for the subspace topology on Y. So what we have done first, we have defined the subspace topology. Then suppose we have some basis for the given big space, and we are defining the basis, the by to be the intersection of all possible base element of x with the subset itself. Now check that this new collection forms a basis for the subspace topology of Y. This is what we need to do. Okay, so you are asking something, Crystal?
No, sir. We are yes, sir. Yes,
Okay,
it is clearly it is also a topology, a basis for
yeah,
B. Yeah.
yeah. So please tell, I mean, try by yourself that how beta y is the basis for the subspace topology on Y. Let's take out time and let me know the solution.
For any open set in X,
Mm,
and any if you take any open set U in X, and you take any point X in that U, we will get some beta X containing the similar to that beta X. We will get here beta X intersection Y. That's the basis element that contains that element, and that will be inside that U intersection Y, sir.
correct. Good.
Uh, Simply we are natural proof it
It's
comes.
correct, correct, right. Okay. So, uh, so this is what regards subspace topology and Brunt topology. So look, now there are some theorems which are actually analogous to the reanalysis thing. So I mean, so so the theorem is as follows: let Y be a subspace of. So whenever I wrote Y is a subspace of X, this means what? X is a topological space and Y is a subset of X, and Y has given a subspace topology. Okay? This whole thing written as Y is a subspace of X. The theorem is if U is open in Y and Y open in X,
Then U is open in X also
yes. How?
because intersection of two open set is open.
Correct. Yes. Okay. So there is another theorem. Let A be subspace of X and B be subspace of Y. Okay. Now the theorem is that the product topology on A cross B is,
Subspace of product topology of x comma x class y, sir.
yeah,
And guess, natural guess.
it is not
Nice
much
theorem.
easier. Yeah, is same as the product topology on A cross B inherits as a subspace of X cross Y. So okay, so try it by yourself first. So we have A and B subspaces. So A cross B has given product topology. Also, A cross B thought can be thought as a subspace of the product space X cross Y. Now the question is that are these topologies same or not? The answer is yes. Of course, naturally, as I mentioned. Uh, okay, but just prove it. Take your time and let me know. You don't need to use anything extra. Whatever the definition we have seen, only you need to use those things. We no need to use extra anything. Okay. Take your time and try to solve. Okay, so what's the chat here? So open sets of suspect topology are open in a given space. Yeah, that's correct, of course. And what about the converse? I mean, of course, the converse is common. Converse, whatever that. Think about the converse also.
Open.
Got it? And let me know. So converse means what? What you need to prove? So what we need to prove first? Tell me.
We have to prove into two parts. First of all, whatever the open set, if you take in A cross B,
Yes.
that open set is
Yeah.
a
That open set has to be. We need to show that open set
yeah
has to be.
that open set W is equal to is nothing but U. Uh, that is
So
the
okay. So first of all, let for the writing convenience, let tau one to be the product topology on A cross B, and let tau two be the southwest topology A cross B. Now we need to check tau one is equal to tau two. Correct. So now tell me how to proceed. Please don't be silent. Please tell if you have any confusion. Please ask also. So what we need to do? We need to tau one into tau two, right? So first we take an element from tau one means what? We take an element for the product topology on x cross y. So let W be tau. Okay. So this implies what? And let of course let x comma y belongs to W. So this implies what? X comma y belongs to U cross B subset of W, where U open in X, sorry, U open in A and V open in B. Correct? Now we need to check the W belongs to tau 2. Okay. Now A is a subspace of X, B is a subspace of Y. So this implies what? U can be written as U dash intersection Y intersection X, where U, sorry, it should be Y, where U dash, sorry, it should be U dash open in X, and V can be written as V dash intersection B, or V dash open in Y. Do you understand these two lines? Why we suddenly wrote this? Look, U is open in Y, open in A, and A is a subspace of X. B is open in B, B is a subspace of Y. And what was the definition of product topology? Sorry, subspace topology. The subspace topology, the open sets are defined as all possible intersection, or all possible elements of form U intersection Y. Okay. So any open set can be written as U intersection Y by definition. Now U is open set in A, which is subspace of X. So U can be written as U dash intersection A, but U dash is open in X. And similarly, V can be written as V dash intersection V, where V dash is open in Y. Do you understand?
yes sir. Carry on, sir. Thank you, sir.
So U cross V is nothing but U dash intersection A cross V dash intersection V. This can be written as U dash cross V dash intersection A cross B. And this thing is open in X cross Y. So U cross V can be written as intersection of an open set of X cross Y with A cross B. So this implies what? U cross V belongs to tau 2, right? That is U cross V. Yeah, just tau 2. So I mean that's so this is the one direction, and
One
this is the
direction is over.
yeah, and the converse. I mean the converse direction that is. I mean so this is what tau one subset of tau. So this is done, and tau two subset of tau one it is actually direct. So there is nothing to do here. You understand? You understand? Okay. Okay, understood properly. So now, okay, now let's come to the very natural thing, namely closure, closed sets, midpoint, and those things. Okay. So the definitions are almost same as I mean definitions are obviously the same as the reanalysis, but for the sake of simplicity, let us record those definitions and those theorems. And theorems are also very much analogous with the reanalysis and the matrix. And after going through this, we shall discuss the problem that has been asked by Ajay in the chat.
Thank you, sir.
So now, once again, let's go back 2 years. Can you wait? আচ্ছা তুমি কি ওকে মটরশুঁটি ভাজা করতে বলেছো নাকি? হ্যালো, হ্যালো, হ্যালো। হ্যাঁ, তুমি ওকে মটরশুঁটি ভাজা করতে বলেছো নাকি? ওকে কি মটরশুঁটি ভাজা করতে বলেছো নাকি? ও হ্যাঁ হ্যাঁ হ্যাঁ, রাইট। ও ও আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে, হ্যাঁ হ্যাঁ হ্যাঁ, ওটাই জিজ্ঞাসা করার জন্য ফোন করলাম। ঠিক আছে ঠিক আছে, নাও, বুঝেছি, অত কথা বলবেন না। নাও। Okay. So, so first definition is closed set. Closed set is defined as complement of open set. I mean, there is nothing to say. Then there is something known as closure. Let A be a subset of X. Then closure of A is defined to be intersection of all closed sets containing A. This is the closure. And the theorem is that A is closed if and only it is equal to its closure. Okay. And the same thing, this definition closure is written as smallest closed subset of X containing A. Okay. Sorry. A. And there is another theorem which is analogous to the reanalysis. This theorem is, look, in the Southwest topology we have seen that some set U is open in Y if it is an intersection of an open set X with the subspace. So same thing happens with the closed set also. Let Y subspace of X and then F subset of Y is closed if and only if F can be written as F dash intersection Y, or F dash is closed in X. We are not discussing the proof here. I mean, this is kind of directly coming from definition only. Okay, please try it by yourself. Okay. So this theorem tells us how to get the closures in the subspace. Okay. And I mean, look, the closures are defined. So I mean, okay, the way in which the closure are defined is similarly the interiors are defined. Okay. So let A subset of U, then interior A is the largest open set in X contained, and this is same as union of U open in X and U is inside A. Okay, this is by the open set, and the theorem is that A interior sub of A sub of A closure. Okay, there is nothing really much to tell about this. And okay, and there is another theorem is that X belongs to a closure if and only if uh, every open set U containing X U intersection A non-empty. I mean, this thing we have seen there also real and symmetric space, but there is nothing to say. And the same thing can be written as basis. Okay, and okay, so okay, so now let's get to the question that Ajay has asked in the chat. Let me look at the question. So the question is, closure of 0, 1 and the cofinite topology. So the question is the following. Closure of 0, 1 in so how do we? So look, what is the cofinite topology? What are the open sets? How does it define? It's open set of the form R minus. Oh, sorry. So it is contains all those U subset of R, such that R minus U is finite or or. So this implies what? This implies in cofinite topology, if subset of R is closed, if and only if it is finite, right? I mean, proper subset is closed if and only if it is finite, right? Correct? I mean, from definition, it's coming. Now, closed 0, 1, it's contained anywhere, closed 0, 1 closure by definition of the closure, okay? Now, the thing is, this is a closed set anyway, And if this is the proper closed set, then it has to be finite, but closed 0, 1 is not finite. So this closure of 0, 1, this closed set has to be whole of R. So let me repeat the argument. This is a closed set. So if this is a proper subset of reals, so this implies this thing has to be finite. But this closure contains opens, I mean that 0, 1 which is not finite. So this closed 0, 1, I mean this 0, 1, its closure is whole of R. So that's why this is the whole real line. Do you understand argument? Do you understand the argument? Okay, I hope everybody understood that. If you made out, you can unmute yourself and please ask. Okay. So, okay. So there is one theorem. Look, in case of reanalysis, you have seen. In case of matrix space, also you have seen that. Um, okay, so in case of reanalysis into the matrix space, there is a notion of convergence of a sequence. Okay, so that whole notion exists in topology also. So let me write down the notion in the topology. Okay. Okay, the thing is that I could not see the chat actually. So if you have any doubt, please unmute yourself and ask. Okay. So please Ajay tell which portion you did not get the idea. Ajay, please tell of which portion you did not get the idea.
Sir, the first question itself, do we have, can we define a norm over any vector space?
I mean, once again, I mean, we are discussing about this question. Suddenly, from here, how we come to know?
Sorry, sir.
So, I mean, first tell me, do you understand this argument? Tell me, do you understand this argument?
Yes, sir.
Yes, sir, I understand, sir.
Okay, okay.
Any finite set is closed set. So every element is limit by yes, sir.
Okay, so you are asking some question. Please now please repeat your question.
Sir, how to find it? Its interior.
How to find it? Good question. Actually. So, hmm, so look. So let's try. First, you try to guess. Okay. So first of all, interior has to open. Then it has to lie inside open 0, 1. Correct. Okay. and whatever the interior be, its complement must be open, right? Sorry, its complement must be 5, correct?
Yes, sir, it is open, so its complement must be finite.
Yeah. So I mean, look. So if so look, so if the interior is of uh, okay, so if uh, okay, so since complement must be finite, so this means what? So this thing is a proper subset of open 0 1. First of all, okay, it's a proper subset. Now we need to determine,
Here,
yes, 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 please tell.
its complement is not finite actually. Open rule 0, comma 1's complement is not finite.
No, look, we are in the cofinite topology, right? Cofinite topology, any set is open if and only if its complement is finite, right? Open 0 interior is open by definition, so its complement has to be finite because we are in the
Hmm.
cofinite topology.
Okay,
Understand?
okay.
Yeah. So first of all, so since complement has to be finite, so this thing has to be proper subset of open 0 1. Correct?
So it's interior is empty.
Yeah, it's a good guess. So suppose the interior is non-empty, then what happens?
It's a subset of open rule 0, comma 1 anyway. But its complement is a
No, it
subset of.
is no. Here I am saying that it is a proper subset of open 0 1. That's what I'm saying. It's a proper first. Okay. So there's a first observation. Now your guess is correct. It's empty. So how to do it? You only need to use the fact that it complements finite. Now tell me.
Sir, we are taking, sir, where we are taking the complement in the R or open rule 0, comma 1, sir?
Complement means complement in R.
R, okay.
Yeah, your guess is correct. It's finite. Now tell me how to do it. Think about it.
Sir, here, if you if you take any open set in R in
Yes.
cofinite topology, its complement is a finite set. So it can omit only finitely many points of R and has to contain all the points of R. Any open set will be of this form only.
Yes.
In open rule 0, comma 1, if you take any point x in open rule 0, comma 1,
Yes.
the open set containing that point cannot be a subset of 0, comma 1
Why?
because that contains the entire, almost the entire R excluding few points of R. So that cannot be a subset of open rule 0, comma 1.
Correct. Correct. Right. Very good.
So none of the points of open rule 0, comma 1 is the interior point. So
Yes.
interior of this set is empty.
Correct. Very good. Very nice. So okay. So in this way, you need to determine some unknown things. Okay. Yeah, it's tricky. First, you need to guess, and you have done it correctly. Very good. So some of you has asking a question regarding norm, plus something like that. Please repeat. Some of you were asking, giving some kind of norm. I can remember. For the question, please repeat. Please repeat the question.
Sir, that first assignment question, first question, sir. How do we define norm in any vector
Okay.
space?
First, tell me one thing. Is the answer of the first assignment has been released?
No, sir. Sir,
So
don't need to, sir.
then I can say sorry.
The okay.
Because it is strictly mentioned to each of us that unless and until the assignment solution has been released, till now we can't speak anything about.
Okay, sir. Okay, nice. Actually, we want to get. How do we define? Actually, the answer is true, but how do we define the answer? Where we know, but how do we
So,
define the norm?
hmm. So have you read non-linear spaces?
I know somewhat.
Okay, so um, okay, so look, so idea is as follows: any element can be written as finite sum of basis elements in unique way, right?
Yes, sir.
Okay. So we are getting some coefficient, I mean alpha 1, alpha 2, alpha n corresponding to each element of the vector space, right?
Yes, sir.
And then using that base element you can do some multiplication so that the ultimate final answer becomes positive. You can do something like you can take the sum of modes, you can take multiply, you can take the sum of squares also, so that the answer will become positive, right?
Actually, we can define many norms like
Yes, right, there are many norms.
Euclidean norm, norm
Yes,
one,
correct.
one norm, two norms,
Yes,
many norms we can define in
yes,
the
yes,
fashion.
you just need to do only one, anything, at least one, that's all.
Uh, but sir, if we consider any infinite dimension vector space,
That's no problem. Anyway, the infinite dimensional vector space, the linear combination includes, I mean, involves only finite basis elements, right?
okay, sir.
So yeah, I mean that's it. So there is no effect in the sum itself, right? Because there is a finite linear combination, so only finitely many coefficients are there. So rest of the thing is zero. So don't. So there is no problem with the infinite sum, right?
Okay, okay, sir. Okay, sir.
Yeah.
Okay, okay. Thank you, sir.
Okay, so in the topology also there is a notion of convergence of a sequence. Okay, so let me. So first, anybody please tell what is the notion of convergence sequence in real analysis or in metrical space? Tell me.
Um, a sequence xn, we say it converges to a point x. Whenever we take some open set around x,
Hmm.
almost all the points of the sequence must be inside that open set around that x, excluding some finitely many points.
I mean that is the visualization. What is the exact mathematical term? Almost all
That
means what? I mean exact mathematical
that
term.
actually it almost converges to, it goes near to x, in the
No, no,
metric.
I mean, even mathematical term, I mean, it goes near to x, that is for visualization purpose. So what is mathematical term? Mathematical
Given
expression.
any epsilon, then we can find a stage capital N, so that after the stage, almost all the terms of the sequence will be the epsilon about of that point x.
Yeah, correct, correct. So the same definition here, but here, of course, the epsilon will not be. will epsilon has no play in the topology, because in topology we don't have any notion of distance, right? We don't have in topology on open set, right? So the definition slightly changes here, and it is thin. So let xn be a sequence in X. Then xn, we say that xn converges to X if for any open set U containing X, there exists a natural number K such that xn lies in the open set for all n greater than equal to K. So this is the definition of convergence of sequence, not topology. I mean, essentially both definition and topology really the same, but here we can't use the epsilon thing. Understand? This is the definition. You get it? I mean, if you have any issue with the understanding my hand, please ask me. Due to some issue, I can't write it straight line in the graphic tablet actually. So this is the definition of conversion. Okay, I should back with 2 minutes. হ্যাঁ ভাজা কি বলছিল ওটাই করবো যেটা কি বলছিল, হ্যাঁ যেটা বলছিল সেটাই করবো। হ্যাঁ ভাত খাবো। হ্যাঁ 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 হ্যাঁ।
Sir, what is the question, sir?
So this is the definition of convergence of sequence topology. So okay, so in real analysis in metric we have seen one theorem, namely any sequence can converge at most one point, right? The same thing holds in topology, provided the space is Hausdorff space. So, I mean, okay, so first of all, tell me, have you seen the word Hausdorff space previously? Or something like Hausdorff condition, something like that? Have you heard it previously or seen it somewhere else? Still?
The space is Hausdorff
Yes.
if given any 2 points, distinct points, we can we will have 2 open sets containing those 2 points and disjoint open sets.
Correct. Yes. So that is the definition of Hausdorff itself. Okay. In the topology. So the question is that, so theorem, so the theorem is that in Hausdorff space, any sequence converges at most one point. So how to do?
Uh, Suppose if it converges any 2 points from x and y, we can
Yes.
have two disjoint open set, but the sequence cannot be in two disjoint open sets at the same time. Excluding many few points of the sequence, almost all the points of the sequence must be in that open set as per the convergence definition, but it cannot be in the two disjoint open sets. Either it should be here in this open set or in that open set. So in the Hausdorff space, any sequence cannot convergent more than one point.
Very good. Very good. Nice. Okay. Very good. So yeah. Okay. So in matrix reanalysis, we have said another type of thing theorem is that any singleton set is closed. In reanalysis, you have also seen matrix space. I hope you have also seen if you have done matrix space previously. The thing is, any singleton set is closed. The same thing holds in the Hausdorff space. Every finite, I mean, the finite set also closed in the analysis also, right? Here also same thing. Every finite set is closed in Hausdorff space. So look, the thing is that you have to show that every finite set is closed, and union of finite union of closed set is closed. So it is sufficient to prove that a singleton is closed in a Hausdorff space. How to prove it? Do you understand what to do? You need to do finite set is closed, but finite set is finite. So finite is closed is closed. So you need to only prove that singleton set is closed in a Hausdorff space. So do just go along with the definition, you will get the answer. Please try it. And if you already know the answer, please admit yourself and tell the solution. Think about it and take it. Yeah, please tell.
Let us prove the singleton set X is closed.
Yeah. Okay.
Instead, we can say X complement is open.
Yes.
Take any point in X complement.
Okay.
The given space is Hausdorff. So
Yes.
the taken point in X complement Y, we
Yes.
can separate X and Y by two disjoint open sets. So the
Okay.
point Y in the X complement is an interior point to X complement. So X complement is an open set. So X must be closed set. Uh,
Correct. Very good. Nice.
Thank you, sir.
So okay, so there are some easy theorems, but let's record it here. There is product of two Hausdorff spaces. Please tell how to do it. I mean, it's obvious. If you can just tell the argument.
Let us let us take 2 points in the product space, sir. Let the points be x1 comma y1 and x2 comma y2. We have to find two open sets so that
Yes,
disjoint open sets containing these 2 points.
correct.
Yeah. Uh, Clearly, these 2 points are distinct. Um,
Yes.
so one of x1 may not be equal to x2, or at least y1 may not be equal to y2.
Um,
These are all two distinct
okay.
points.
Yeah. So let assume, I mean, without loss of generality, assume that x1
x1 is not equal to x2.
x. Yes. Then
Corresponding to x1 is not equal to x2. So capital X is Hausdorff space.
yes.
So corresponding to this x1 and x2, there will be some u1 and u2 disjoint open sets u1 and u2 containing these 2 points x1 and x2.
Correct. Then
And uh, corresponding to that y1 and y2, there will be some open sets. Take
fine.
any open set, no problem,
I mean,
sir.
there is no need to y considering y and y2 itself. You have just only considered x1, x2 not equal. I think it is sufficient.
Yes,
Because you
sir.
can consider the set u1 cross y and u2 cross y, and intersection is empty. So here also the intersection is empty, and this contains x1 y1 and this contains x2 y2. So we are done. Understand?
Thank you, sir.
Yeah. There is another theorem is that subspace of Hausdorff space. Theorem is that subspace of Hausdorff space is Hausdorff. So how to prove it?
Similar proof only, sir. If you take two distinct points in the subspace x comma y,
Yes.
now consider uh, these 2 points in the whole space. There will be two distinct open sets, two disjoint open sets u and v containing these 2 points. Now take u intersection this subspace
Yes. Got
and
your point.
v intersection this the subspace, and these open sets
Right. Right.
are
Very good.
disjoint.
Yeah. Very good. Correct. So now, okay. So now let's go with some exercise. There is, I mean, the theory of what is burned over. Uh, so this is one very important and very useful exercise actually. So x any space is Hausdorff if and only if the diagonal is closed in x cross x. You understand the question? The given space is Hausdorff if and only if the diagonal x cross x is closed in x cross x. So how to do? I mean, just you need to proceed along with the definition of open set, closed set, Hausdorff, etc. There is nothing extra to this. Let's first try it yourself.
Similarly, sir, here we can show that its complement is open.
Hmm.
Let us take any point in its complement.
So let.
Yeah. Uh, correspond here x and y are distinct, so we will have, because it is not in the diagonal, so we
Yes.
will have two disjoint open sets containing these 2 points. Here
Yes.
here sir, u cross u that contains the point x comma x. U cross u contains the points x.
Yes.
uh, uh, we will give another open set containing this x comma y. uh, Actually, I have to show that x comma y is an interior point of right. Sorry, sir. Let me give you an open set containing this x comma y. Um,
To show that x cross y belongs to some open state which is contained inside our delta complement, right? Point is that whatever is written on the screen, x cross y belongs to some open state already, which lies outside the delta itself also. Just recognize it just.
Sorry, sir. Become blank. Uh,
Okay, no problem. Look, the thing is x cross y belongs to u cross v. Okay. Now the thing is that since U intersection be empty, so U cross V lies outside delta, right?
yes, sir.
And this is what you need to show. X cross Y belongs to U cross V, which lies outside delta. So this is what? Delta complement is open, right?
Yes, sir.
Understand?
Yes, sir. Yes. I have to. This U cross V should not have any point of. It should be a subset of delta complement.
Yeah, correct, correct. And it is coming in naturally because the intersection is empty. So U cross U and V has no common set. I mean, sorry, common point. So this is one thing. So X house drop implies this thing is open. Now show that delta complement open implies X is house drop. Now show that X house drop. How to do? What to do? The same thing. Start by, I mean, start with the definition. Try it yourself first. I mean, look. Look, we need to check x's house. Okay. So take 2 points from x which are not same. So this is implemented over x comma y belongs to delta complement. We assume delta complement is open. So this is implemented over x cross y belongs to elements of the form u cross v subset delta complement. So this is implemented x belongs to u, y belongs to v, and x cross u cross v subset delta complement means what? This implies u intersection v empty. So this is what we mean by house droplets, right?
Sir, super nice proof, sir. Online proof. Thank you, sir. Actually, earlier, thank
Okay, so this is one question. Was okay. So there is one other explain. Show that A union B whole closure is equal to A closure union. Okay, I for some of you maybe it is easy, but for some of you may not be not. So try to do it. Try to prove it. That for finite case, closure of union is union of its closure. Prove it. Take your time. Please do. I'll let you know. Please do.
you. Sir, in analysis,
Yes.
A union B, the whole closure,
Yes.
we have to show both are equal. So we have to show the limit points of A union B, the whole closure, is a limit point of the limit point of A union B is nothing but the limit point of either A or B. If you prove this one is enough, sir. Yeah. Let X be a limit point of A union.
You may use the limit point, but without using the limit point, you can also do it. We are also doing this.
It's difficult then.
No, it is not difficult. Just think about it. It is not difficult.
Okay, sir.
Take your time and think about it. Look, uh, one second. Look, the thing is, anyway, A subset of A union B, right? So A closure subset of A union B whole closure. So this implies what? A closure union B closure subset of A union B whole closure. Correct. This is one set. Also, A union B is a subset of A closure union B closure. Now, A closure union B closure is a closed set containing A union B, and A union B whole closure is the smallest closed set containing A union B. So this implies what? So this implies what? This implies A union B whole closure subset of A closure union B closure. So this thing and this thing gives the answer. Gives the equality. Do you understand?
Yes, sir.
So look,
Yes, it is
in the
closed, sir.
yeah, correct. So in the union of two sets, so in the finite union place closure and union distribute, but in arbitrary union it may not be. So the thing is,
Nice
you
proof, sir. I have not seen in that way. In topological way, nice, simply shown. Nice proof, sir. Thank you.
so the thing is that in the reanalysis also you have seen examples that in finite. I don't know whether you have seen the reanalysis or not, but the thing is in arbitrary union case that the closure and union not necessarily distribute. So give one example where closure and union does not distribute in the arbitrary union case. Provide and give an example. Look, the thing is union of A alpha closure subset of union A alpha whole closure. This side is in obvious for any type of union, but it's a proper sub. It might be a proper subset in case of arbitrary union. So give one example where this thing is actually a proper superset of this thing. Provide one example. Think about it.
Sir, Q closure is equal to R. But if you take a single, with respect to standard topology, we can consider.
Correct. Very good. Nice. Correct. So A alpha is equal to Q unit. Correct. Right. So prove that A cross B whole closure is equal to A closure cross B closure. If you know the proof, if you can already guess, just please tell. If you don't know, think about it. Take your time, think about it, and tell.
Sir,
Yes.
A cross B is a subset of A closure cross B closure. A cross B is a subset of,
Yes. Okay.
but the right hand side, A closure cross B closure is a closed set, right, sir?
Correct. Correct.
So if you take the closure in the left hand side,
Mhm. Well then,
that is also a subset of that right hand side. This is
okay. Yes, this is one side. What about converse?
this one side, sir. Similarly,
Think about it. So thing is converse possibly not direct. So we need to check what? We need to check A closure cross B closure, subset of A cross B closure, right? So what to do? So take a point x or y belongs to A closure cross B closure. So this is not what x belongs to A closure and y belongs to B closure, right? And we need to show that x comma y belongs to A cross B whole closure. That is, if we take an open set U cross B containing x comma y, we need to check that U cross B intersection A cross B non-negative. This is what we need to show, right? Now the thing is that since x belongs to U closure, so this implies what? This implies U intersection A non-empty, and similarly B intersection B non-empty. Sorry, non-empty. So this implies what? U cross B intersection A cross B non-empty. So this is the argument. You understand? I mean, so this is non-empty. This is what we need to check actually. So this is what x comma y belongs to A cross B closure. You understand the argument?
Yes, sir. Thank you, sir.
So there is. So in previously we have seen one theorem that in a Hausdorff space any sequence can have at most one. Can converge in at most one. So the thing is, we will see one exercise where the space is not necessarily Hausdorff and a sequence can converge in many points. So consider R. Consider reals with cofinite topology. Consider the sequence xn is equal to 1 by. Question is to what points does the sequence xn converge? In R with cofinite topology, we consider the sequence 1 by. Now we need to check in which points the sequence xn converges. First think
To
about
all the points, sir.
okay, how?
Take any point x in R and
Yes,
take any open set around x.
yes,
That open set can omit only finitely many points
okay,
of R. So that obviously omits finitely many points of the sequence also.
yeah, correct, very good.
So that open set contains finite, excluding finitely many points. Sorry, that open set contains almost all the points of the sequence.
Correct, very nice.
So this is a definition. So that x is a limit point of the sequence converges to x.
Yeah, yeah, I understand.
So
Very important. Finished. Okay. So that's it for the protobology and that's it up to the closure input. Now the next topic is continuity. But okay. So before going to that, please, if you have any question in the from his third class, also you can ask it. If you have any question, please ask. Or if you have any question from a previous session, also you can ask me here. Okay, just tell me one thing. Since some of you is not in the last session, so are both of you from BSc or both of you from MSc?
yes, sir.
I mean, you guys are from BSc or you guys are from MSc?
Sir, I didn't get your question, please, sir.
Yeah, I mean, you are a postgraduate student or you are a undergraduate student?
Sorry, sir. I'm very sorry. I'm a faculty, and first time I'm attending such a online class. Actually, I have done some few NPTEL courses,
Mhm.
but this time I have applied two courses. One is this point topology, another is graph theory. But I never have attended this discussion session. It is very useful. Actually, I could. I am a faculty and very old, around 40 years old, sir. 39 years old.
That's good to hear. Faculty of which college you
Government Engineering College, Bodinayaknur from Tamil Nadu, sir. Working in the Government Engineering College last many years and have no touch with the graph theory as well as in point topology. Never have touched those subjects, and these are all comes under FDP also. We can have some analytical thinking and visualizations, everything gone, sir. So just wanted to study these courses again.
Okay, got it. I mean, so just I want to know just curiosity. I mean, what brings you here? I mean, is there any connection with this new thing with your faculty or those things, or you are doing it by only your self interest? I mean, is it somehow connected with your just job profile, or you are doing it by yourself?
I'm doing it by myself, sir.
Okay, that's good. That's good to hear, actually. Okay, so
Sir, the session was so nice. Thank you, sir. And Ajay has put, he's from PG, sir. Ajay Jangra.
okay, okay, okay. So since there are 5 minutes left, also, I mean, if you have any question, you can ask me. I mean, I can start continuity, but today it's too much actually. So if you want to ask me, I mean, since 5 minutes left actually, so you can ask any question if you have actually. Okay, so there is one question. Yeah, please ask, please ask. If you have any question, please ask, or else I will ask one question. Okay, so there is one question is that show that R with finite complement topology. No, no. So the question is that R with finite complement topology, not house type. Okay, so the thing is that in the last exercise we have seen that in the sequence extend converges in infinite many points. So using that we can say that it is not Hausdorff, but from directly can we say is it possible? Can you please prove directly that R with finite complement topology is not Hausdorff? Directly from definition. Just try. It is easy.
Yes,
Just
sir.
try.
It is not cost of, sir, because if you take any two distinct points,
Yes.
uh, we will take any neighborhood containing this point x as well as that point y.
Yes.
This cannot be disjoint because
Yes.
this open set U containing X will omit only finitely many points, and the
Yes.
another one open set B containing Y will omit only finitely many points.
Yes.
So, uh,
I mean, you are there. You are almost there.
uh, so the intersection must be in an infinite set actually, sir. How to say it omits only finitely many points. It omits only finitely
Yeah.
many
So
points.
that so
Con-
yes, right. So technically, the thing is, if U intersection V is empty, so this implies U complement union V complement is whole of R, but U complement finite, V complement finite, so it cannot be whole of R. That's the argument.
thank you, sir. Thank you, sir. Nicely done, sir.
So I mean, this type of argument is actually very technical argument. You don't need to think about those intersection finite or not. Whatever it comes automatically.
Hmm.
Okay. So okay, if you have any question, you can ask me. We have a few minutes left only. I mean, I so there is no point of studying continuously. If you have any question, please ask. Okay, there is one definition for the limit point, but the thing is, in reality, in topology, there is no use of limit point as such. So simply I skip this, and really it is of no use uh, concerning the topology perspective. Okay, and yeah, yeah, that's it. I mean, yeah, I mean, or next day we can start continue. Please tell me what portion is uh, going in the honors auspicious club?
Sir, I will study, and in the next session, I will come up with many questions and doubts,
Yeah,
and will solve the assignments. Actually, from today onwards, only started seeing the assignments. Let me go through it, and thank you for the nice session, sir. Nice active session. And the students of our country has to make use of these like such sessions. They cannot
yeah,
have such discussions of from the IITians. They don't know the value actually, and even me now only I come to know the value by attending such discussions. Thank you,
it's
sir.
it's my pleasure. It's my pleasure.
Thank you, sir.
So do one thing kindly. In the chat box, I have submitted one Google form link. I am sending the chat again. Please mark your attendance. Okay, because I need to share
Done,
this to together.
done, sir.
Oh, thank you. Okay, so let's
Okay, sir.
see on next week. Thank you.
Good night, sir. Good night.
Yeah, bye.
Good night, Ajay.
Okay.